Thank you for watching Knowledge Academy. Alright, I'm sharing a screen which is definitely showing you a potato and it says directional derivative and gradient. So before we start this topic, let me give you a brief introduction of what we're going to discussing about. What is mean by directional and what do you mean by gradient, right? Derivative, you know that is a rate of change or change per unit another variable, right? Change per unit another variable. It could be time, it could be another variable. So what is a gradient? We're going to talk about that. Before we do this, I'm going to be taking an example for this potato. So let's suppose if someone is asking you to cut the potato with a knife. So you're taking a knife, I'm going to make a simple version of knife. You make a knife and then chopping this potato into this direction, right? And basically this potato is going to be look like this, half piece, and the other half is going to be look like somewhere here. Now, this is a phase where you cut this, right? This is a phase where you cut the potato. Now, what is a directional gradient? It means potato, I consider this potato is, this is not a smooth surface, so I'm going to call this is a surface. And when you talk about the directional gradient, what exactly talking about? You're taking this curve, which curve? This curve, right? Taking this curve, like a red color curve. Maybe we can color this curve with something else. Maybe just this portion is white color. So you're taking this curve, right? And ask yourself if you want to make a vector. Maybe you're gonna make the vector like this, right? And you're gonna take this vector, maybe you're gonna grab this vector here, maybe you're gonna grab this vector putting over here, right? And every point in this curve, you can see this vector is going to be look different. Maybe this point is going to be look this way. Maybe this point is going to be looking this way, right? So the basic idea is that you get an idea what is a surface. You take any surface, you have to cut the surface to get a curve. To cut the surface to get a curve. So do you want to get the curve? And after the curve, you need a point. This point, maybe this point, maybe this point. You need to get a point. And after that, what exactly you're going to be doing? You're going to be talking about how fast or slow this curve, change. How fast or slow this curve change. This is exactly the directional gradient. So really what you need a direction, means you need a vector. Right? Derivative, you want derivative, but you have bunch of variables. You have x, y, maybe you have z. So you cannot take the variable. So you need a vector first thing. So in order to give you the vector, I have two options. I can give you a vector like a vector. I'm going to give you the vector like this, I, j, k. Or I can give you points like this point and this point, and you can make your own vector. Right now I'm talking about this is a vector. Right? This is a vector I'm talking about. And this is a vector I'm talking about. And this is a vector I'm talking about. And then derivative. So you cannot take the whole derivative. So you're actually taking partial derivative. Right? And the gradient. Gradient means magnitude. So really what you need a vector. You need a vector. You need a points if you have a point, and then you need a partial derivative, and then you take the magnitude. But one thing we forgot, we need partial derivative, right? A partial derivative at certain point, at a point. So this point and the points is two different things. Points means I'm going to give you 2 points to make the vector, but this point is the point which I'm talking about. So you're going to find the value at particular point to writing, to determine the partial derivative of particular point. So let's talk about that. This is a basic idea of this one. Maybe you can cut the potato in this way. Maybe you cut the potato this way. And you know what? The best idea is that I don't want to give you this curve. I'm going to just give you 2 points here and here. So you're going to give me the vector. And underneath the vector, you're going to be making this curve where the potato is tracking, or any surface. It's not really going to be potato. It's going to be any surface. So you're going to take this point, and this point is a point you're going to need to find the partial derivative of this surface. So this surface could be 2D, could be 3D. Let's talk about the mathematical explanation of how it's going to be look like. Okay. Let's do it. I'm calling directional derivative and the gradient vector. We already talked about this one. And pretty much as examples is going to be making like this. You're taking a surface, or maybe a patch of a surface, right? You're making a surface, a patch of surface. And after taking this patch, you need to find out at this point, maybe you find at this point, I want the partial derivative or gradient at this point. So really what it means, you need to get two vectors or two direction. It's changing. One is this way, one is this way, right? This way, the way you're going to be changed, you're going to call be dz over dy, right? dz over dy or dz over dx. But really, and it's you're going to be calling this one, you're going to be calling dz because it's changing in this direction, or dy, right? And this one you're going to be calling dz or dx. Really, you think about it. Here, y considered as a constant. Here, x considered as a constant. Because this line, this yellow line, the one I'm just highlighting right now, x is constant, okay? And if you want to be writing this gradient, you're going to be write like this, du, right? And this is a point where you're taking you just try to make the point you're going to be dropping. So you're going to be dropping this point on the surface, like this. And at this point, you're going to be taking a vector, like a little vector, right? This is a vector which when you're going to be cutting. And this vector is a u vector. U vector, I can call it A, B. Remember, I gave you vector through points, through A. You did vector coordinates. So this time I just gave you vector in a vector form, okay? The function of this is going to be f, x, y, and I'm going to be calling them z, right? This is my function. And what I'm going to be doing, I'm going to be taking this function x naught, y naught, x naught and y naught. I'm going to be writing like this. But before than that, I'm going to be writing a limit form definition of this directional derivative, and it's going to be function x plus h a, right? h a. That is my, technically that is my equation or parametric equation, x equals to x naught plus at. Remember, here I'm going to call him h because h is my multiplier this time, and I'm going to say is comma y naught plus hb, right? That's my function. I'm going to adding, right? And really what you're doing, you're just taking the function and adding a little bit portioning to this, and you're going like this way. So if you have a curve, you're going little bit in X. And if you have a curve in Y, you're going to be going little bit on Y, right? So this is Y and this is X. This is what exactly we're doing here. Minus the function X naught comma Y naught divided by H. This is we used to write a derivative in a limit form, right? But I can also write this theorem in a different way. And that's what we're going to be using most of the time. F has a directional derivative So I'm going to be writing like du directional derivative of this function. And you're going to be taking partial derivative of x, right? And then partial derivative of y. But this is my function. Don't forget. We used to write like this. And I'm going to multiply with unit vector x component and unit vector y component. And that's about it. That's all we have to do in directional derivatives. Okay. Now, sometimes this vector is given in the form of coordinate. Sometimes this vector is given in the form of a unit vector. Right? You can also write alternatively. You can also write this one in an alternative way. You can write, let me just do it here. So everything is written in one place. You can also write like this: du f x y equals to fx x y I plus fy x y j. So you're writing the vector in a unit vector format, and then take a dot product of the unit vector cos theta I, sorry, plus sine theta I, sine theta j. Right? You know what we have to write like this. You can also write this way, right? The third way you can write is pretty much same thing. You just write in a different format. You can write this gradient f. So now what you learn is one other thing is that what is this? Basically, I'm going to call it, it's a gradient symbol. Gradient symbol. I'm going to explain this thing in a minute. Let's do it. The term gradient means grade, right? Can distinguish. Grades can distinguish who is good, who is bad, who is superior, and who is, not superior, or basically not functioning well. Or maybe it depends on you want to be quantifying. Really, a gradient means you want to be quantifying. You cannot say that this this student is have a better grade than others. You just not enough. You need a number, right? You need a ladder, maybe grade ladder or percentage. Same thing gradient means. Gradient is a technique, but in the end of the day, you need a number. That's why I say gradient means magnitude. When you do the gradient, so you're going to be writing like gradient of f. You're going to be writing like this. X, so you have a 3D or three-dimensional function. So it means the surface look like complicated surface, and you're going to be writing like this. Remember, this is a symbol, so you can also write like this. And what does that mean? It means you're going to be writing this. You're taking this function and taking the partial derivative. You're taking the partial derivative of this function with respect to x, y, z. For example, this function I'm going to be writing like this. Some books writing like this, some books writing like a partial derivative symbol, some books like writing probably like this. And the reason they just don't call it partial because it's a gradient so obvious. It's a mathematical technique using all the time, so they just says is superior than you call it gradient and use a symbol and then just done with this. So I'm going to be taking an example of how we calculate the gradient, right? So the gradient of, I'm going to give you the function, the gradient of this function. The function is giving x plus y squared plus c cube, right, at this point, 3, 4, 5. Okay. So first thing first, you're going to go and ask yourself, how can I write this gradient? You're going to be writing like this. Just function. You can also write like this, and then you can also maybe writing. This is the first time we're writing this gradient, so we just have to follow every protocol. Maybe we can skip the steps later. You can also writing this, and I'm going to be writing the function. Another thing is that every time you're writing, right, every time you're writing these parameters, like in the denominator y, z, x. So basically, you're writing like a partial derivative, or you're writing this. Really, it's telling you besides x, everything is constant. That's what it means. You have 50 variable. If you're writing d over dx, means besides x, everything is constant. All the 49 variable is constant. So really, dx means this y and z is constant. This y means x and z is constant. Z means y and x both are constant. Okay. So we're going to take the partial derivative pretty much at this point, and the partial derivative of this one would be 1, then 2y, 3z squared, right? And we need to find at a point, so we're going to substitute the values. So it's going to be 1, then 1, 2, this is 2, 3, 4, 5. So I'm going to be adding, there is no x quantity, so I'm going to be adding just 1. The other one will be 8. The other one will be 5, 5, so 75, right? Z squared, 25, 25 times 3 will be 75. So this is pretty much what I got. And that is my gradient, right? Now you're going to say that, well, this is not really a number, right? It's not a number. But the thing is, it means we are moving a little bit less in x, a little bit more in y, and z we are moving a lot. So maybe if you have any function like this, the function is coming, or if this is a z-axis, the function is coming and then changing like this. But if you look at the y, is basically maybe coming and just moving a little bit on the y because this is y. So really, this is a change in all three axes, and it's telling you which way the function is more sensitive. Which way the function is more sensitive. You have a coffee cup. You're putting with the black coffee, and you're putting a little bit creamer, that much. and the coffee turned into a little bit, milky or coffee color, right? Brownish or whitish. But the thing is, if you have this much coffee, you're adding creamer and you're adding too much creamer, three creamers, coffee completely change. But what's happened if you're adding more black coffee, a little bit more, it doesn't change much. It means the taste of a coffee or the color of a coffee is dominated by creamer, and creamer is my prominent variable. Same thing in function. Here, my z is a prominent variable. So if you change anything in z, function quickly change. If you change anything in y for x, I mean x is a muted one pretty much, and in terms of z is 75 versus 1. And that's exactly what we want to know. So, and this strategy is people using, you know, all the time for different aspect, for different kind of application is very helpful. Okay. So let's take other examples of this topic. Of this function, find the direct derivative of half xy of the function is this. Add 1, 2, this is a point is given in the direction of u. Right? And the u vector is could be given in any way to you. There are many different ways that u vector would provide it to you in the question. Sometimes they give you in a unit vector form, sometimes they give you in a vector form, sometimes they give you in a just an angle, right? Because you only need the direction. So just like you have like a potato, I told you want a directional derivative at this point, right? Point P, which is 1 and 2 at this point. 1, 2. You're asking yourself, I want a directional derivative. Where? Here, here, here. Which direction? You have to pick the direction. So really, I don't need a big vector or a small vector. I can give you just a unit vector, or I can give you a big vector. It's not going to be making any difference. Even though I give you a big vector, like a long, full size magnitude vector, you can convert that into unit vector and use in your formula. Okay. So let's take a look what we can do with this question. Will be -2, right? And fy for function fxy equals to -1/2y. Okay. So we're going to be writing theorem, right? That's what we're learning earlier. And theorem is that d, the directional derivative of u at unit vector. Du means directional derivative of a at unit vector in the direction of unit vector for this function. So really it means directional derivative of function f in the direction of unit vector u. This is exactly what it means. Somebody writing like this, it means in plain English, that's what they're saying. Directional derivative of a function fxy at or in the direction of a unit vector u. I'm going to call the whole function here, right? And if you want to mathematically, you're going to be writing. We already learned about this theorem, I'm going to be writing like this. Take the partial derivative of x function with respect to x and cos theta. Cos theta means is a unit vector, x component, right? And really what we are doing, I'm going to show you in a minute what we did. And here is a sine theta. Okay, if I go back, so what I did, I really apply this, right? And I take the dot product. So what I did, I take this guy, multiply by this guy, and I times I dot I means they have both cos 0, and cos 0 means 1. So I'm going to be writing f x x y cos I dot I. This I dot I turned into be 1, so I don't write 1. So I just leave these two things together, plus this one multiply this, j dot j, which is 1. So I'm not going to be writing the 1. That is exactly what I did here. Oops. So I'm going to continue this. We can wrap up this one. So minus 2x cos theta plus minus y over 2 sin theta. Here I'm going to be taking the du of function at this point. So I'm going to substitute the values. Right? And the function is also given in the problem. Right? The problem is given. That is my theta. Really, this is my theta. So I'm going to write it if theta equals to pi over 3, theta equals to pi over 3, x equals to 1, y equals to 2. These are the things I'm going to substitute into the value. It's going to be minus 2, right? And times 1 is going to be 2. And cosine pi by 3 plus minus 1 pretty much, because if we substitute 2 times divided by 2 is going to be 1 with minus sign, and then sine pi by 3. If you take this further, simplified is going to be minus 1 and plus, I think it's both are minus. It's going to be minus 2. Minus, and if you further, simplify this, you can add and subtract them, and the answer would be minus 1.8666. Okay. Pretty much that is my answer for this gradient. Another example, two variable function, right? Find the gradient of fxy equals to y ln x plus y square xy square at the point this. Now, pretty much this is a complete function, but you notice one thing, I did not give you any vector. So basically, you don't have to worry about it. The only thing is that when you give me the answer, you're not going to give me the answer in a magnitude. You give me the answer in a magnitude plus the unit vector, right? The unit vector form, right? And how I'm going to solve it? Just watch this. In this problem, my answer will not be in a magnitude because magnitude is not given for the unit vector. or the direction is not given. Only function is given at certain point. So what I'm going to do, I'm simply just taking a partial derivative just like I used to take it partial derivative and then substitute the value of the point or the coordinate 1, 2. So what I'm going to do, I'm going to write here fx y and then fy with respect to y and with respect to x. I'm going to take the partial derivative, so it's going to be y for x plus y squared. This one is respect to y, so it's going to be ln x plus 2yx, right, or 2xy. And I'm going to be just writing simply the partial derivative of these functions. And really, the I and j is not given. Remember early in previous function, in the previous example, this guy used to be cos theta I. The cos theta is not given, so I'm assuming 1 here, 1i plus 1j. That is my unit vector. Right? It is not given, not given. And technically speaking, unit vector means magnitude equals to 1. So if the magnitude equals to 1, I should be writing 1i, comma, 1j, comma, 1k. This should be my unit vector, right? That should be my unit vector all the time. So I'm just writing like this way, and I'm going to be substituting the value which is given pretty much in this case. We already find out. One at 2, I'm going to be substituting, so it's going to be f1 2 equals 2 over 1 plus 2 squared I plus ln 1 and 2. Everything is given here really, and I think that's the part j. I further elaborate is going to be 2 plus 2 to the 4 plus 2 6, so it's going to be 6i plus ln 1 0, and it's going to be 4j, and that is my, this is my answer. Let's do a couple of more problems. Okay, let's do this problem, very relevant problem. Find the directional derivative of a function two y squared at a point, and just give the point in the direction from P, and in this, like I mentioned earlier, Sometimes they give you vector in a vector form, sometimes they give you vector in a coordinate form, and sometimes the vector give you in a unit form, right? So -340 and then q is 0, 1. Those are my two coordinates. Let's start it. The key here is going to be fractional derivative. So everything is given here, so I'm expecting my answer should be a number, right? And that answer is technically number, but number came from a vector. Just like I showed you the vector, you can find the magnitude of a vector. So I'm expecting in this question, the answer should be a number because all the quantities are given to me in a quantitative form. So I should not be making any assumption. So my PQ, that is my vector, is given. So I'm going to say is 0 minus 3 over 4 I plus 1 minus 0 j. If I simplified this one, it's going to be 3 over 4I plus j. Now I have a unit vector is given. So my vector is given. Either I can multiply, but I just need a unit vector. So u pq or eq, and this is a magnitude. And if you remember, I told you if I give you a surface like this, and you want the vector that gradient in this direction, this point, you just need a little small vector, which is u. If I give you complete vector, it could be a long vector which is not necessary. So I'm going to be taking this u, and u is equals to 3, 4, and let me just go back. It's going to be 3 or 4 plus 1. If you take it, I think it's 9 plus 1 or 16. And it's going to be 9 plus 16 or 16. Right? And it's going to be 25 or 16. And the whole of the square root, you're going to be saying 5 or 4 probably. Right? So if you substitute the value, you're going to get I. I'm just dividing it directly with 3 over this, and the reciprocal of that one, plus 4 over 5j. Right? And I'm going to be writing here unit vector in the direction of PQ. That is my this is my u vector. Right? Now I'm going to be taking the gradient part, right? And gradient and unit vector both has to be multiplied to find the directional derivative. So I need this part for sure. Six xi minus 4yj. You substitute the value of this. It's going to be minus my 2I plus 0. The y term becomes disappear. And this is my gradient at this point. Since I have a limited space, I can just say it's not directional derivative. I'm going to write here Fractional derivative DUF minus 3 over 4. This we'll be writing like, I used to write like this, right? Remember, I used to write like this, but since we have a limited space, I can add one more point here. I can just write the coordinate of my point dot G. This is exactly the dot product. So really, rational derivative is a dot product. Rational derivative is a dot product. If you remember, dot product or scalar product between unit vector and the gradient vector. So I substitute this one, and it's going to be equal to, we're just writing like the way it's given up on the screen, so we don't confuse. Oh, sorry, J dot 3 over 5 I plus 4 over 5. If I multiply this one, so it's going to be multiplied like this. This term multiply this term dot I dot I. So I dot I means 1 times 1 cos 0, and cos 0 means 1, really. So when you multiply, so 1 times 1 is going to be 1, so I don't write 1. But 9 over 2 minus 9 over 2 times 3 over 5 need to be multiplied, so I'm going to multiply them. 9 times 3 over 10 plus 0, and plus 0. And if I do something, it's going to be 27 over 10 minus 1. Right? And there is a rational derivative. All right, let's review this concept again one more time. So directional derivatives is a gradient is a change, right? Gradient is a change. That change happened in a vector form, in two coordinate form. So somebody gave you two coordinates, like this coordinate and this coordinate, and asking you the change for delta x, delta y, delta z. All you have to do is take two coordinates, x2, y2, z2, and then x1, y1, z1. Really, this change means you're trying to find the change, which is x2 minus x1, y2 minus y1, and z2 minus z1, right? These are the changes you are talking about. You can do this way, or you can do this way. When you do this way, right? When you do this way, what exactly we are doing? We're trying to control the jump. When I say jump, when I try to control the jump, you cannot jump from here to here. You cannot jump. They don't want to be jump you that much. They want to control the jump. What does that mean is, it really means is, if I gave you a point, right? If I gave you a point from, let's suppose, maybe you have a point like, you know, this curve is coming from here to there, and really you want to be dropping this curve and dropping this curve. So this curve is on this axis too. If you go up, this curve is on this axis too. Like maybe if you want to project it here, it's going to be look like here. If you want to project it on the back, it's going to be look like that. So it's a 3D curve. When I say control the jump, what it means, I'm not asking you to go from here to there. I'm asking you to go from here to there in a teeny bitty step. Those steps should be very small, like these steps. So the reason I'm doing this is because I want to control the jump so I can compare it better, or I can watch it better, or I can analyze it better. So rather than I can go from here to there, I'm gonna going like go a little bit, then go a little bit, then go up, then go forward, then go up, then go forward. So I can follow this curve a little bit better. Mathematically, I can do this. And these small steps you call dx, dy, dz. And if you do these steps together, right? Few steps doing together, you're actually making three stairs. These stairs, one in this direction. So one in this direction, you're gonna make the stairs. One stairs you're gonna make in this z direction, right? So you're gonna make these z direction stairs, and here one stairs you're gonna be making in this direction. So you are making three stairs together. So really, it's one stairs, but it's a 3D stairs. One stairs in the 3D stairs in the 3D form, and the domain that you use is you're going to be using this, and you're going to be use a partial derivative for this one. Right? So we learn about that one, and we call this whole process called gradient, right? And that's a thing we talk about. Does gradient have a value? Gradient is a vector, and in a particular direction, when I give you the direction, you actually finding this plus this, right? When you do these two things, you're actually doing a dot product between the two, right? When we do these two things, you're actually doing a dot product between the two. And really, what is a dot product? You're taking this partial derivative dot that gradient vector, the vector we have it here. You can write a vector here, maybe whatever. Now, this is actual math, right? This is actual math, and direction is only a unit vector. So really, when you're writing the dot product between the two, so really is a dot product, nothing but you can writing this dot product. You take this I from here, writing the I, right? And there's a function, but the thing is, you're taking this dot product, but there is a portion of this one, there is I2, so dot I is 1, so that's why you're writing just df over dx, u vector, times, right? So really, if I'm gonna be writing in a little bit expansion form of this, you're gonna be write like this. K, sorry, K and then DC. This is my first vector dot. My other vector is I plus J plus K. And if you multiply the two, taking the dot product, you're going to multiply this to this, plus this to this, plus that to that. Right? So really is one here, one here, one here. So you're writing like this. Times 1, then I dot product, then go to the second one. J dot J. Same thing you do K dot K, but one thing Israel was asking about, where does it go? What's happened to this? This what's happened to this? Remember, this what happened to this I dot I means 1 times 1 cos 0. Cos 0 is 1, so this whole thing becomes 1, because the magnitude of the two vectors I dot I, both vector magnitude is 1, and when you're taking the dot product of two vector having a 1 magnitude, the answer would be 1 times 1 cos theta. The cos theta will be 0 here. Cos theta, the angle is 0 between the two. So cos 0 is 1. So everything becomes 1, and we usually don't write 1. And that's where the I is gone. But then another thing is, which is very important. When you're solving these problems, the answer of this thing should be a number. When you do the directional derivative in a particular unit vector form, the answer should be a. If everything is given in a numerical form, the answer should be a value like 5.3, something like that. Okay. Thank you for watching Knowledge Academy. Please subscribe my channel.